Hello! Today we will consider the structure of the atom and pay attention once again to the subatomic particles that make up the atom, namely protons, neutrons, electrons, but as part of such varieties of elements, their atoms, as an isotope. But first, let me remind you that any chemical element has what's called an atomic mass, which is usually written at the top, and then at the bottom is the atomic number. Which we traditionally write down at the bottom. For each element, we find these data respectively in the periodic table. For example, if we take the element iron, its ordinal number is 26 and its rounded mass of one of its isotopes is 56. Or, for example, if we take the element zinc, its number 30 and the mass of one of its isotopes is 65. What do these numbers indicate? Recall, the serial number or atomic number shows us the number of protons. They will be 26, and accordingly in zinc, its serial number will show us 30 protons. Then subtracting from 56 for iron 26, we get the number of neutrons, and then for zinc, this neutron number will be 35 respectively. The nucleus is made up of protons and neutrons, and so will be respectively for both iron and zinc. But we have still particles, electrons with minus charge, which will be according to the order number 26 for iron, and for zinc it will be 30. Thus, we know from the periodic table that shows the ordinal number or atomic number and that shows the atomic mass, which for the elements we find from the periodic table. As a rule, we round it off. But we know that relative to the atomic mass of any chemical element, if we look at it carefully, its value from the table, we find that the atomic mass is not an integer. For example, for the same iron, this value would be 55 whole and 9/8 decimal places. For zinc, it is also not an integer. Why does this exist? Because there are concepts of isotopes. Isotopes, let's look at the example of two elements, hydrogen isotopes and carbon isotopes. So how will they be similar and how will they be different? The first isotope is a hydrogen isotope with mass 1 and number 1. This kind of hydrogen isotope would be hydrogen, which is called protium. This is the isotope that is most abundant in nature. Then how many protons will it have? In order of number, it will have 1. There will be no neutrons in this atom, and there will be 1 electron. Now hydrogen is number 1 with a mass of 2. It's called deuterium. Such hydrogen will also have protons 1, it will have neutrons 1, and electrons 1. For hydrogen that has a mass of 3, and the number is also 1, this is the third isotope of hydrogen. Its third will have a number of protons 1, a number of neutrons it will have 2, and electrons it will have 1. Then it's easy to see that all isotopes of hydrogen have exactly the same number of protons. Are the number of electrons, and so they will have an atomic number. That is, this atomic number will be exactly the same. Then what is different? They will differ in this case by the number of neutrons. This will be the difference for all isotopes. They will differ from each other by the number of neutrons. So the difference will be in this value of atomic mass and in the number of neutrons. Now I'll remind you that the ratio between protons and neutrons is important because it determines the stability of the isotope. If this number is the same, moreover, if it is integer, such isotopes are stable. And if the number of, for example, neutrons exceeds the number of protons and the criterion is greater than 1.2, then such an isotope is unstable. Hence, we can conclude that hydrogen isotope 3 will be unstable. Let's take the carbon isotope now. So its number of protons would be 6. The number of neutrons is 6 and the number of electrons is 6. For the second carbon, which is less in nature, respectively, it will be 6. Here it will be 7 and the number of electrons 6. Well, now carbon, which has a mass of 14, it will have 6 protons, 8 will be neutrons and 6 will be electrons. As we can see, again they will be similar in the number of protons, they will be similar in the number of electrons, and they will differ in the number of neutrons, and therefore their masses of these isotopes. They will be identical in the number of protons and electrons and in their ordinal number. Let me remind you again that we have a pattern between the number of protons and neutrons, and if the number of neutrons is predominant, then these isotopes are unstable. Here I would like to note that the carbon isotope with a mass of 14 is used for this very reason, to determine the age of certain artifacts. This value allows us to determine the approximate age of this or that historical object by its content, because this isotope is radioactive. It is like a kind of mark that allows us to establish the age of this or that historical object. So isotopes can have certain practical applications. But here I would like to say that some of them are not dangerous for us. These are those that are stable isotopes. For example, hydrogen with mass 1 or carbon with mass 12. Carbon with mass 12 is the carbon that makes up all living things, including our bodies. And hydrogen with mass 1 is in the water that we use as drinking water. But the isotope of hydrogen, for example, the third isotope, is the basis, for example, for the work of our sun. Because just on the sun there is a thermonuclear reaction, thermonuclear fusion, which leads to the fact that the sun radiates. Well, for carbon with a mass of 14, we have already said there is an area of application. It's determining the age of this or that object. So isotopes are important varieties of this or that chemical element. Goodbye.